Welcome to the 3Depict tutorial on doing concentration filtering. Now first of all we're going to start by opening a POS file from the menu here. Now we can see the ions that have been loaded, and they've been loaded with a default colour. So in order to identify these, we can add a range file, which you can open here using the ranging filter. And here we can disable or enable ions as appropriate. And that's just showing the copper ions, which show some clustering. And those are what we're going to be interested in filtering. And we can add a bounding box to that just to make things a bit more clear. And we can also disable the axes using the view menu. Now to do the concentration filtering, we're going to use the spatial analysis filter, and I'm going to disable the auto refresh so that it doesn't calculate as we do things, because this can be quite time consuming. For the algorithm, we're selecting local chemistry, and we have a few different options. So there's the stop mode, the source ions, the numerator and denominator, and these are what are used for calculating the concentration. So first of all, the stop mode, I'm going to select radius and a value of 0.5. And now we can make a selection of the source ions and the ions used for making the calculation of the local concentration. Now here only the copper ions are displayed, and that is because in the ranging tab we disabled iron. So let's enable that again so we can use it in the next filter down, which is the spatial analysis. So now we have iron enabled as a source ion. So that means the results will be reported for all those ions. And we can disable it as part of the numerator, which means the result that's returned will be copper divided by the number of iron plus copper atoms, and that is the copper concentration. Now we have everything set up as we want. We have all the filters in place. We can re-enable auto refresh, and we can click refresh to do the calculation. The progress is displayed in the bottom right hand corner as a percentage, and also on the screen as a progress bar. Now because we have a bounding box on the ranged data, not on the spatial analysis, what we're seeing are the ranged ions rather than the spatially filtered ions. So let's move that bounding box onto the spatial analysis. And now we can see that the results are just grey points, and they don't have any colour associated with them. And you'll notice where the mouse is that there is a little exclamation mark on the spatial analysis indicating a problem, and that is because the data is sampled when we loaded the original POS file. This can help speed up calculations, but when doing cluster analysis or this kind of spatial filtering, we need to disable that because we want to have a concentration value for every single point in the analysis. Now to visualize the concentration, we're going to add an ion color filter, which will color the ions in the visualization based on their value. In this case, this is going to be concentration. Again, because of the bounding box, we're seeing both the grey points and the colored points. So if we move that bounding box, now we can just see the colored points. And here the color bar on the left shows the local concentration of each of those points. And as well as visualizing the positions, we can also show a spectrum, histogram of all the different concentrations, and this shows the number of atoms with the different relative concentrations. By left clicking twice slowly on the name, we can rename that. I'm going to rename this as real data spectrum so that we know which source of data that came from. You're wondering where a lot of our points have gone, but if we change the background color to white, we can see that there are just a large number of points that have a concentration close to 0, which don't show up against the black background. So when you're making your visualizations, remember it's very easy to change the background color. In the spectral color filter, there are also a number of different color maps which you can choose, and these may highlight different features of the values that you're trying to show. When performing spatial filtering, it's always good to use a random comparison to compare the real data set to, And we can do this using the iron transform filter. I've got two iron transform filters here. One of them I'm going to set to translate, and the other one I'm going to set to value shuffle. And that will randomly relabel the values which are stored with the data. By doing 2 long clicks on the name, we can rename this filter to be translate and rename this one to be shuffle. That way we can tell them apart. Now I'm going to copy this analysis using the control and drag to move that onto the shuffle, and I'm going to click and drag to move that onto the translate. Now we have 2 copies of those filter trees, one happening after the translate and one happening after the shuffle, and this will show us the unshuffled data translated in space and the shuffled data in place where it was before. So the 2 results appear on top of each other, which is because I think the iron transform translate didn't have a different value set, so we need to actually move the data set across by 18 nanometers. And then just click refresh to redo that calculation. I can double press space in order to reset the camera. And now we can see the real and the shuffled data set next to each other. Now the color bars are using their own scale, so let's just set the scale manually to be 40 for both. So that's for the real data, and then for the shuffled data we can also change the upper limit and refresh that. And now we can see the real data on the left, which has got some inhomogeneity, and the random data which looks much more uniform on the right. When I copied the filter tree previously, I didn't change the name of the plot, so let's change that from real data to random data. And let's also change the color so we can see it differently. Let's change that to red. And then on the plot list we need to highlight both of those plots so that we can see them. And now we can see clearly a difference in the concentration histogram between those real and shuffled data. And here it looks like about 10% is a good cutoff value for distinguishing between the 2 types of real and random data. So now we have an idea of whether random data occurs. We can filter based on the concentration, and to do this we use another iron transform filter. And this time you'll set the mode to crop value, and here we can set the minimum and maximum values to filter the points by. So I'm going to type in 10%, and where I've added that in the filter tree, the spectral color and the bounding box and the spectrum all have to occur after the iron transform. So we can move the bounding box and we can move the spectral color so that everything is in the correct order, and then refresh to recalculate the data. And now on the left hand side we can see that only the points with a concentration greater than 10% have been kept. And we can see how that compares to the shuffle data set on the opposite side. Now we have the filtered points, we need to export this data set, which we can do using File and Export and select Ions. And here if we click Selected Data, then we can select the filter which we want to export the data from. And the available data is shown on the left. And once we select a filter that has some iron data in it, then we can copy that across to the selection and then save that and give that a name. And I recommend naming it based on the element that you're filtering and also the concentration, so that you know what that data set is for next time. Now let's just clean up the filter tree by deleting the shuffled data, so that's not in the way. Now instead of having the concentration as the value for each of these points, we want the original master charge values, and we can do that using the spatial analysis filter with the EM point replace feature. I'm just going to add another translate filter here so we can see them side by side, and then we can add the spatial filter. This time we'll use the spatial filter with point replacement, and we'll need to choose a file to get the points from. So these are the data points that we'll use to filter this data set. And so we've loaded the filtered data set and we're applying it to the original data set. Now we've filtered that data set using the point replacement, we're going to add a range file so we can see the different ions that have been that are remaining afterwards. And again, we need to just translate this data set over so that it's not overlapping with the previous one. And then just refresh that. So now it looks like we still have a lot of data that looks like it's not been filtered, so it looks like lots of iron atoms that have remained after that. And the reason for this is because in the spatial analysis we left it selected as subtract, so actually we've removed the points that we wanted to keep rather than filtering them. So now if we change that mode to intersect, we can see that looks a bit better. But what we're doing here, because we have replace value selected, it's replacing the value from the data file over the top of the original data. If we unselect that, then we get the correct ions that we needed before. If we add a spectrum to show the result of that filter, we can see we have two peaks for the two different masses. If we click replace value, you can see we actually have the concentration histogram again. So make sure that replace value isn't ticked when you're performing this operation. And that's our filtered data set with the original master charge values for each ion. If you wish to do anything else with those ions, you need to export the ions so you can open them in other programs. And we can do that using the selected data export option. And here we can see the ranged ions. We can select those and then save that data set. And this time I'm going to save it as the master charge because that's what we have stored in that data set.